In this video, we will look at the open source data linkage software RDMP. RDMP functionality can be split into four main areas: data loading, data curation, cohort generation, and data extraction. First, let's look at how we install the software. In order to follow this demo, you will need a version of SQL Server. SQL Express is free and will suffice. RDMP is hosted on the GitHub open source code repository. On the main page, you can find links to the user manual, the frequently asked questions, and the changelog. The changelog shows a history of all the changes that have been made to the software, including features and bug fixes. In the Releases section, you can download any version of the software. Download setup.exe and run it. Once the application starts, select Set Platform Databases and enter the location of your SQL server. Make sure to tick Example Datasets. This will create a number of test datasets for us to explore. Let's look at how we curate our datasets. You can see a list of all the datasets loaded by RDMP in the Catalog Collections. If we open the biochemistry test set, we can enter a description, an acronym, and set any flags, like deprecated or internal. We can also enter descriptions for columns. If we change the description of the Chi field, then the system will automatically detect that Chi appears in other datasets and ask if we want to sync the description. In this case, it appears in 5 other datasets. RDMP supports basic graphs for understanding the data and for testing filters, which we will see later on. In this graph, we can see all the biochemistry test codes taken each year. There are a lot of series in this chart. We can reduce the number by setting a top to limit the number of test codes shown. We can see that the test code column has a number of filters defined. These are ways of reducing the number of records matched when building cohorts or extracting records. We can test the filter works by combining it with the test codes graph. We can create a new filter, for example one that matches HbA1c test code. Again, we want to test this filter with the graph to make sure that it's correct. The hospital admissions dataset doesn't have any graphs yet. Let's look at how we create a new graph. We will be creating a graph that shows unique patients by year. We start by adding the admission field. Then we change the count so that the y-axis shows only the distinct chi numbers. Finally, we set the axis to the admission date and put a sensible date range on it. Next up, let's look at how we control dataset governance. We do this through governance periods. In this case, let's create a period for 2019 to 2020 for Tayside and Fife. We can choose which catalogs it applies to. We can also attach any relevant files, such as letters of approval or dataset lists. governance report, we can see which are covered by governance. If we generate a governance report, we can see which datasets are covered by governance and which are expired or don't require it. The report shows the dataset period as unknown. We can fix that by running the data quality engine. We start by setting up validation rules for our columns. Let's set the type to not null and add a chi constraint. Each rule has a severity level, which we call consequence. For the health board column, let's create a regular expression of T or F. When we run the pre-execution checks, we can see that there is an error about a missing column and time field. Let's go back and fix that by setting which column provides the dates for the records. There is a warning about pivot column, but we can address that later. The DQE graph shows that all the chi records are failing validation. This is because they are randomly generated and do not match on chi check digit. We can go back into the DQE rules and we can add a pivot on health board, as well as removing the chi validation rule. Now when we run the engine, we can see the results are split by health board, T and F. The DQE results are stored in a longitudinal database where all records are The DQE results database stores a longitudinal record of all executions run, so we can look back at previous results. Now that we have run the DQE, we can see that the dataset period in the governance report is now filled in. We can also generate a more detailed report. This is called a catalog metadata report. It will run any graphs that are marked extractable, as well as fetching useful information about the dataset, such as the row count, the number of unique patients, and the column descriptions. A vital part of curation is recording which datasets are used for cohort generation and data extractions. In this case, we see that project number 123 has 3 configurations that include the biochemistry dataset. We can see which other datasets were released in the extraction, as well as which versioned cohort identifier list was linked in that extraction. If we want, we can clone that extraction and run it again, for example, to provide an update for a research project halfway through. In the extract, we can see the number of unique patients and row count, as well as the descriptive metadata on the dataset. If there were any filters on the records extracted, they would also appear here. In the output file, we can see that Chi has been substituted for an anonymous GUID mapping. RDMP supports extracting to both CSV and directly to database, but for this demo, we will restrict ourselves to CSV. Let's look at how we get new datasets into RDMP. If the dataset already exists in SQL Server, Oracle, or MySQL databases, we can simply create a new catalog by referencing that table. Let's import the hospital admissions dataset from the Oracle database. We can tell RDMP which column contains the linkage identifier, in this case, Chi. We can also choose what extraction category each column should have. Since we already have a Chi column, we can import the description from the other dataset. We can create a new graph like before. In this case, let's create a graph of admission dates by year. When we view the data, we can see that the SQL generated is appropriate to the Oracle database management system. If we don't have a database table yet, and we want to import a flat file, we can do so. First, we pick the destination database. Let's use MySQL this time. Again, let's set the extraction categories. If we want to, we can restrict which projects a dataset can be used with by tying it to a specific project. We can see that the system has loaded the records and created the appropriate data types in the MySQL database. If we look at the top 100 records, we can see that the record number column appears to be a GUID. If we run an aggregate on the column, we can see that there are no counts greater than 1, so it is indeed unique. Let's set the primary key on the table to prevent duplication in future. The import file functionality is for one-off loads. If we want to create a routine load that we run every month, we have to create a data load. Let's create one for the hospital admissions dataset. To start with, we need to give the system a location on disk to store SQL scripts, load files from, we can copy the file we originally bulk inserted into the forloading directory. Let's make a couple of changes to it so that we can tell the DLE has worked. We can change a primary key value. This will result in an insert of a new record. We can also change a couple of other values in different records. These will result in updates since they are not part of the primary key. In order to run the data load, we will need an attacher to read the CSV file. When we run the attacher checks, we can see that it expects us to provide a separator, the table we are trying to load, and a file pattern to match. First we set the separator to comma, then we choose the table we're loading. Finally we set the file pattern to star.csv. Now when we run the checks, we can see they pass and we are ready to load the data. The data load has crashed. If we double-click on the error, we can see why it is unhappy. In this case, there is a problem matching the columns in the file with the columns in the table. Specifically, the HIC data load run ID column is in the file, but not in the database table. Assuming we are happy to ignore this field, we can edit the attacher and add it to the ignore list. Now when we run the data load, we can see that there are one insert and two updates as expected. If we view the logs, we can see a sample of which records have changed. Here is the new record we inserted, and here are the updated records. Let's look at how we generate cohorts and perform linked extractions. If a cohort is coming from another system or is provided directly by the researcher, we can simply import the list. We will create a new extraction project and give it an extraction directory and a project number. We will also have to provide a name for the cohort. The system has audited the path where the file was loaded from, and the date and the user. To load the file, we will need to select a pipeline. If we edit the pipeline, we can see which component is responsible for allocating the release identifiers. We can also set it to null if we want to allocate the release identifiers ourselves later on manually. When we run the engine, we can see that the system is unhappy because there isn't a column called Chi. The private identifier column name has to match the column name of the cohort source we are storing in it. This avoids confusion and allows us to handle any number of private identifiers, not just Chi. We can fix the problem by setting the header name explicitly in the source component. Let's double-check the file to make sure our assumption is correct. Although there are duplicate Chi numbers, these will automatically be discarded. Now that we have successfully run the pipeline, we can see the cohort has been saved and allocated release identifiers in our cohort database. We are now ready to do a linkage and extraction using the cohort by creating a new extraction configuration in the project. We need to select our cohort, as well as the datasets we want to be extracted. When we run the extraction, we can see that the linkage occurs on each dataset, where the file is produced, along with the descriptive metadata. Results are extracted only for the patients in the cohort, and the records produced are anonymous. If we don't have an explicit cohort file, we can build one using the RDMP Query Builder. Let's build a configuration starting by intersecting patients in the biochemistry dataset and the demography dataset. When we run this query, we can see how many patients are matched in each dataset, as well as the intersection. Since these queries are likely to take a while, we should create a query cache which will store indexed temporary tables for each dataset. Now that we have a query cache, we can generate graphs for the matched patients. We can also view a sample of the matched records. Let's add a filter to biochemistry to match only HbA1c test results. Now when we run the query, we can see the number has dropped to 89. This new identifier list has also been automatically updated in the cache. We can view the matched records and see that only HbA1c has been returned. If we graph the results for these patients, we can see all the tests these patients have had. This lets us see what other test codes are popular among patients with HbA1c test results. Let's add a restriction to the demography dataset to match only Tayside and Fife records. If we graph this dataset, we can see that there are many young patients. Let us throw out any patient with an age under 18. Now that we have changed the meaning of the cohort sets, we should update the descriptions. This will make it easier for future data analysts to understand the configuration. For some set operations, the order is important. Let's look at how we can add an exclusion criteria for patients in the carotid artery scan table. When we are happy with our cohort, we can commit it. Let's pretend that this is a refinement of the previous cohort we loaded from the file. Again, we select a pipeline. This will run the query and save the matching patient identifiers into the cohort database. Now when we look in the cohort database, we can see the old deprecated cohort and the new version. Let's update the extraction configuration cases to use the new cohort and document this in its description. Although the cohort was built using only specific test codes, there is no such restriction on the records extracted. We can see in the metadata document that there are no filters. We can add the same filter to the biochemistry dataset in the extraction. Or we can use a different filter. For example, we could extract both HbA1c and creatinine. If we try to release this configuration, the system will tell us that the live configuration does not match the extracted files that are stored on disk. In this case, both of our new filters are missing. We will need to rerun the extraction in order for the new files to be generated. Once we have run the biochemistry dataset, the files on disk will match the new filter criteria. This will allow the datasets to be released. The release process will collect all the extracted artifacts and place them in a single directory that can be zipped up and sent to the researcher. If we view the logs, we can see a hierarchical representation of all RDMP activities, including extractions. In the extractions view, we can see the number of rows produced and the SQL used for linkage. This includes any filters used in extraction. Since we have released the configuration, it now appears frozen. We can either leave it frozen or clone it ready for when we want to use it again next year.